This is AQA A-Level Chemistry. We're looking at the Year 13 Carbonyl Chemistry topic, and this is video number 3. Going to recommend, as always, that you pause and have a go at the activities for yourselves, find out what's going well, find out what you need to develop and focus on. So, in this video, we're going to introduce carboxylic acids and esters, going to look at some of their properties, and we're going to focus on their nomenclature as well. So let's jump straight in by having a go at naming some carboxylic acids. So on the first one, skeletal formula, I've got 1, 2, 3, 4 carbons. That means the name is based on bute. It's a carboxylic acid, which means it ends in oic acid. So we're looking for butanoic acid. On to the second one, I've got 3 carbons in a row. So that means it's propanoic acid. Now a carboxylic acid will always be the higher priority. It will always be carbon number 1. That means if it's the only functional group, we don't need to number it. Okay, moving on, let's take a look. Another skeletal formula here. And we have got 1, 2, 3, 4, 5 carbons in a row on this one, which means the name is based on pentanoic acid, but actually we've also got a methyl group coming off. The methyl is coming off the second carbon, which makes it 2-methyl pentanoic acid. And on to the next one, we have got a carbon chain of 1, 2, 3, which means the name is based on propanoic acid, but on this we've got a chloroside chain, and that's on the third carbon in the chain. So 3-chloropropanoic acid. Got some more examples for you. On here, I've got 1, 2, 3, 4, 5 carbons in a chain. That means it's pentanoic acid with the C double bond OH on the end, the COOH, but I've got an alcohol group coming off in the third position. Now, I can't use ol because I've already got oic acid as the suffix, so I need to use the prefix that we use for alcohols, which is hydroxy. So 3-hydroxy pentanoic acid. On to the next one, my longest carbon chain is 4. That means it's based on butanoic acid. I've got 2 alcohol groups here, so that's dihydroxy, 1 in the second, 1 in the third, 2,3 dihydroxy butanoic acid. We're going to move on, look at 2 more. On the first one, I've got 3 carbons in the chain. That means it's based on propanoic acid, but I've also got an amine group coming off. Now, I can't use the amine suffix because oic acid is already there, so it becomes 3-aminopropanoic acid. And another amine here with a carbon chain of 4. That's butanoic acid. My amine is on the second carbon. That's 2-aminobutanoic acid. Some more examples for you. And what we've actually got here is a carbon chain of 4, but we've got a carboxylic acid on each end. That makes it a dioic acid. It's 4, so it's butandioic acid, but you will not get the mark for writing down what's here. You need the magic E in dioic acids, just as you do in nitriles and diols. So butane dioic acid. On the second example here, it's 3 carbons in the chain, it's 2 carboxylic acids, so this one is propane dioic acid. Again, that E is absolutely crucial. Okay, some physical properties. Are carboxylic acids soluble in water? Well, if I draw out a generic carboxylic acid here, and I start to think about where I could get into molecular forces, I could get hydrogen bonds formed where we see them here. The fact that we've got hydrogen bonds means that we are going to have solubility in water, but not always. That's only going to be true for shorter chain lengths. In fact, it's only true for the first 4 carboxylic acids up to butanoic acid. Anything beyond that is insoluble. And the way to think about this is, if you've got a very long carbon chain, a long carbon tail, it's going to be very difficult to disperse that through water molecules, so it won't dissolve. So longer chains are insoluble. Okay, how do melting points of carboxylic acids compare to their corresponding alkanes? And by corresponding alkanes, we're comparing MR. Well, they're much higher than the corresponding alkane. Let's compare butane to ethanoic acid, which have not massively dissimilar MRs. There's hydrogen bonding present in carboxylic acids, but there are only van der Waals forces present in the corresponding alkane. Hydrogen bonding is stronger, so the melting point, boiling point is higher. We're now going to focus on naming esters for the remainder of this video. What is the functional group of an ester? Well, it looks a little bit like a carboxylic acid in the sense I've got a C double bond O and an O, but instead of there being an H here, we have another alkyl group. So let's look at some of these in action. Whenever you're naming these, you look to what the alcohol would contribute when we're making an ester, and we'll learn more about that next time, but that's to the right of the single bond O, and then the end of the ester name comes from the carboxylic acid that made it. So let's take a look here. I've got 1, 2, 3, 4 carbons coming from an alcohol, butan-1-ol. That means that here I am starting with butyl. The remainder of the name comes from the ion that we yield from the acid that makes this ester. So you can see here, if I replaced this butyl group with an H, it would be propanoic acid. That means that what we're left with is a propanoate ion, so it becomes butyl propanoate. On to the next one, again colour coding to show what's come from the alcohol and what's come from the acid. What we get here is a methyl group coming off an ethyl group, so open brackets methyl close brackets ethyl, and we have got a benzoate ion, so methyl ethyl benzoate. Let's look at another couple. Once again here we look at what comes from the alcohol to the right of the single bond O. That's going to be ethyl, and we're left with 1, 2, 3, 4, 5 carbons in a row on our carboxylate ion, so that becomes ethyl pentanoate, I should say. And then I have got on this next one propyl propanoate. Now let's have a go at drawing some, see what you can do with these. So for A, I've got my methyl group coming here to the right of the single bond O, and my ethanoate ion that I've highlighted in green. For ethyl pentanoate, for the second one, I've got my pentanoate ion, and I've got my ethyl group coming off from the single bond O. For C, phenyl ethanoate, well, phenyl comes from phenol, so I've got my benzene ring here, and my ethanoate ion, similar to what we saw in the first one. For D, it's ethyl hexanoate, so we have got the ethyl group and the hexanoate ion. We've got ethyl benzoate, well, there is my benzoate ion from benzoic acid, and here is my ethyl group. And finally, phenyl benzoate. Now, if you've looked at the aromatics topic, you'll be aware of the quirks in naming, about when to use phenyl, when to use benzoic. And in this case, the benzoate comes from the benzoate ion in benzoic acid, and the phenyl comes from the phenyl group in phenol. Couple more just to name to get a bit more practice. What would these be? And we have got a methyl group, and we've got a methanoate ion, so methyl methanoate. On the second one, I've got an ethyl group, and I've got propanoate, so it's ethyl propanoate. On the next one, be really careful, because this has been drawn the opposite way round. Here, I've got an ethanoate ion, and here I've got a propyl group, so propyl ethanoate. And final one, back to the normal way round, the conventional way round of drawing them, I have got propyl propanoate. So finishing off with some properties of esters, what do we know about them? Common properties of esters is they have very fruity smells. Think of pear drop sweets. They're often used as flavourings or smells in sweets, in perfumes, things like that. They're also very volatile. That takes us to the end of this topic, or this video, sorry. Thank you for listening, and goodbye.